This is CPM Calculus Chapter 5, Number 16. Without your graphing calculator, sketch f of x and then algebraically determine where the function is increasing, decreasing, concave up, and concave down. Also, list any maximum, minimums, and points of inflection. Alright, so let's go ahead and sketch this graph. Right here, we're given f of x, and it's a piecewise defined function. We have two different pieces, and we see the transition happening at x is equal to 2. So let's go ahead and draw our axes. There's our x-axis and our y-axis. Here is x is 2. Okay, so for x is less than 2, we have this graph here. And what we see is that this is basically a parabola, x squared, that is shifted inside the parentheses. Minus 2 means to the right 2. Shifted right 2 units outside the parentheses. Plus 3 means up 3. The negative here means reflected across the x-axis. Right? So let's go ahead and draw that. So first of all, we have a parabola that's going down, but the vertex, instead of at 0, 0, is right 2, up 3. So 1, 2, 3. And we have a parabola that looks something like this, right? Except we're only defining it for x is less than or equal to 2. So let me go ahead and erase the right side. Okay? And we have a parabola that goes down here. And at x is equal to 0, this becomes nothing here. This is 0. I'm just testing, well, what will it hit? What will the y-axis intercept be? So 0 minus 2 is going to be 2 squared, or negative 2 squared, which is positive 2. But I mean positive 4. You take a negative, and that's going to make it negative 4 plus 3 is negative 1. So it's going to hit. So it's going to be a parabola that hits our x-axis here, right? Maybe let me draw a little better. There we go. So there is this piece of our function f of x. This piece for x is greater than 2. We also have a parabola, right? This one is shifted to the right 3 units and up 2 units. Okay, so here we have shift right 3, and this we have up 2. So we have right 3 units, up 2 units. So here's our vertex, and it's going like this up, right? But we're not going to draw it past, we're not going to draw it to the left of this region here, because that's where the transition happens. Well, at x is equal to 2, we're going to plug in 2 minus 3 here. It's going to be negative 1. Squared becomes positive 1. Plus 2 becomes 3. So at 2, this one is going to be an open circle. At 3, but they meet there, so it actually is going to be like this. So, and because they connect, and it's a continuous function. F of x doesn't have any gaps. It has the shape of a downward parabola and then an upward parabola. Okay, so now so we're still not using a calculator in this. We want to algebraically determine where the function is increasing, decreasing, concave up, and concave down. So let's go ahead and use a different color. Increasing. So I'm not doing it algebraically. We'll do that in a second. But just graphically or geometrically looking, the function is increasing until it hits 2 here, right? So it's increasing from negative infinity to 2. Not including 2, because here it stops, and then it starts increasing again from 3 here forever to the right. So union 3 and to the right to infinity. Decreasing next, we see it's only decreasing from 2 to 3. Everywhere else it's increasing. So we can write that 2 to 3. We're excluding the endpoints. Concave up, we can go ahead and write that. Concave up, well, here it's concave down. Concave up, it's this region here of this parabola, and we can see that it starts at 2 and goes to the right forever, from 2 to infinity. Concave down, right? Concave down is this region, right? And that is starting at negative infinity and stopping when we get to 2. Alright? So looking at the graph geometrically, it's easy to figure out these 4 regions: increasing, decreasing, concave up, and concave down. Also maximums, minimums, and points of inflections. Well, where do we have a maximum? We have a local maximum right here, right? Here's below it, here's below it. So we have local max at 2, 3. This point is 2, 3. This is not a region from 2 to 3. It's a point 2, 3. We have a local minimum right here at 3, 2. That's a point again, not a region. And a point of inflection. Do we ever change concavity? So we're going, this is concave down, this is concave up, right? So you might think, well, maybe we have a point of concavity here, but this is kind of like a cusp. So let's go ahead and say point of inflection. Let's say there are the point of the change. Let me explain it this way. In concavity, if change in concavity happens at a cusp, right? At this point 2, 3. And this, so therefore it's not an inflection point. Alright? Alright, so that covers all the bases. Let me just see, but then how do we do it algebraically? So quickly, to show you how to do it algebraically, to do it algebraically, we want to look at the first derivative and the second derivative, because the first derivative is going to tell us things about increasing and decreasing. So let's go ahead and do this. Let's use a different color. So algebraically, that's a little hard to see. I'm going to use blue. Okay, so increasing and decreasing, we want to look at critical points. Critical points happen when we look at f prime of x. Okay, f prime of x, so let's go ahead and find the derivative of this, right? We're going to bring that 2 down, so it's going to be negative 2 times x minus 2 plus 0 for x is less than or equal to 2. And this region, this piece of our graph, is going to be 2 times x minus 3. I'm using the power rule. Plus 2 becomes 0 for x is greater than 2. So this is the derivative. Let's go ahead and simplify that, distributing that negative 2. Distributing this positive 2. Okay, so this right here is the first derivative. And as you can see, we're going to look for where this equals to 0, right? Where it's equal to 0 are the critical points. So remember that it transitions at 2. But let's go ahead and see where it's equal to 0. So f prime of x equals to 0 are our critical points. Right, so let's go ahead and find where those are. We have, in this piece, we have negative 2x plus 4 equal to 0. Solving for x, subtract 4 from both sides. We get negative 2x is equal to negative 4. Divide by negative 2, we get x is equal to 2. Okay, and that is within our region, so that is one critical point. Another critical point is where this is equal to 0. So we have, for this right here, same thing. 2x minus 6 equals to 0. Add 6 to both sides. Divide by 2. And this is greater than 2, so that falls within that region. So these are our 2 critical points. Okay. So critical points show us an interval 2 and 3. These are our critical point interval. Okay, so we're going to look to the left of 2, in between 2 and 3, and greater than 3 for whether or not our graph is positive or negative. Sorry, whether or not f prime of x is positive or negative. If it's positive, if f prime of x is positive, that means it's increasing. If it's negative, it means it's decreasing. So we pick any point to the left of 2. I'm going to pick 0. Okay, so f prime of x, we're going to plug 0 into f prime of x. Okay, so let's go ahead and plug it in. So if we plug 0 into f prime of x here, let me use a different color for a second. So 0 is less than or equal to 2, so we're going to plug it in here. So we're going to get 0 minus 2, which is negative 2. Negative 2 times negative 2 is positive 4. So this is going to be positive throughout this whole region. The critical points show us that at this point, we might go from positive to negative. It might stay positive and positive, or it might go positive, negative, positive, whatever it is. To the left of 2, it's always positive. Between 2 and 3, it's always the same thing, whether that's positive or negative. That's why it's a critical point. Okay, the regions between or to the left and to the right are going to be consistent, positive or negative. So we see it's positive there, so that means increasing, right? So we even had that here, negative infinity to 2, right? From looking from here, this region, negative infinity until 2 is positive. And again, the critical points, we exclude those, so those are always going to be open circles. Anyway, from 2 to 3, plug in any number from 2 to 3, so I'm going to choose 2.5. 2.5 is greater than 2, so I'm going to plug it here. 2.5 minus 3 is negative 0.5. 2 times negative 0.5, if you use your calculator, it's just 2 times negative 1/2, which is negative 1. Okay, so that's going to be negative. Finally, we're going to choose any point here. I'm going to use 4. You can use 5, you can use 500. I'm going to use just simple ones. X is greater than 2, so 4 is greater than 2. We're going to use this piece of our f prime of x. Plug in 4. 4 minus 3 is 1. 1 times 2 is 2. 2 is positive. So this tells us right here, algebraically, our function is increasing from negative infinity to 2, right? It's positive, and from 3 to infinity, right? Or union, or is the better word. I shouldn't say and, I mean also. But this region or this region are places where f prime of x is positive, thus f of x is increasing. Okay? Decreasing, f of x is decreasing from 2 to 3. That's because it's negative here. Okay? So I'm not going to rewrite these answers. I'm just showing the work on how to find them algebraically. Concavity, we want to look at the second derivative test. So this was the first derivative, and then we looked at positive, negative, positive regions. Well, let's also look at f double prime of x. Okay? Let me use blue to do this. So f double prime of x is just going to take the derivative of our first derivative. Okay, so looking at our first derivative here, using the power rule, the derivative of this is going to be negative 2, and again it's for x is less than or equal to 2. The derivative of this is positive 2 for x is greater than 2, right? And is it ever equal to 0? No, it's not, right? But we have one critical point, the transition from this region to this region, right? This one already included that transition point, so we didn't add it in. But here we have 2. We know to the left of 2 is negative, and to the right of 2, 2 is positive, right? So this shows us the concavity is negative from negative infinity to 2, and positive from 0 to infinity, right? And negative concavity means concave down. We just said negative infinity to 2. Positive 2 shows as concave up. Concavity is positive from 2 to infinity. Okay? Alright. So there's how we find, what did we find so far? We found where the function is increasing, decreasing, concave up, concave down, all algebraically. Looking at the local max and minimum, we want to go ahead and see, well, where are our critical points, right? X is equal to 2 and x equals to 3. When f prime of x is equal to 0, that's where we have a max or a min. So x is 2 or x is 3, we have a local max and min. So you have to do, though, is then go ahead and plug the x value into our original function, not f prime of x or f double prime of x, but plug in x is 2, and your output is going to be 3, right? Plug in x is 3, and your output's going to be f of 3 is 2. Your y value is going to be 2. So these 2 points are found by plugging in the critical points of our f prime of x. Okay? And so we have all of these information, and the change of concavity happens at a cusp, so there's no inflection point, and we are done with CPM Calculus Chapter 5, number 16.